Today what we have here is kind of a follow-up from a previous video I did from the Florida integration bee where we had something really similar to this, except the bounds were minus n to n. In that video we dealt with the case where n was infinity for the bounds, but we also dealt with the integer case. So take away the pi if we just had minus 2024 to 2024. But what I kind of skipped over in that other video was the non-integer case, and that's exactly what we have here. These are definitely not going to be integers. But what I want to do here, because we have the floor and the integral, and the floor always is going to resolve to an integer value, and what seems to work best is if we break up our bounds where the upper bound and the lower bound are separated by just 1. That seems to work pretty well and gets us the simplification we need. Now, doing that's not going to be entirely possible because, like I mentioned earlier, the bounds here are not, what we have right here are not integers, so there's going to be a little bit of a problem at the end. So to get started with this, for the first integral, we'll go from minus 2024 pi to some integer value, which we'll call minus n here. And so I'm defining n to be an integer. I did this on my calculator really quick, not that we really need it, just kind of out of curiosity. If you take the ceiling on this lower bound, you get this minus 6358. So now we have an integer for the upper bound here. And inside of our integral, we're going to have the floor of x. In this case, it's not going to round us down to the lower bound because the lower bound is not an integer. It's going to round it down 1 from minus n. It's going to be minus n minus 1 here. And then for the next integral, it's going to be more like what we usually do, where now the lower bound is minus n, and then for the upper bound, we can write it as minus n plus 1. Now both of our bounds are integers. When we have the floor of x, when x values are between two integers, it's just going to be the lower bound. So this one's going to be minus n. And maybe let's just do one more really quick. So for the next one, we got minus n plus 1 to minus n plus 2. The floor takes us down to the lower bound, minus n plus 1 dx. Now, of course, we're going to have a whole bunch of terms in here. I'm not going to write out 48 terms or whatever it is. But eventually, we'll get to this last integer one, not the total upper bound, but we'll get to one that's going to be like n minus 1 to n. The floor is going to take us down to this n minus 1 value. And then for the next one, here we're going to be going from n, finally to our upper bound, 2024 pi. But here the lower bound is an integer, floor of x takes us down to the lower bound, and so this one is just going to be an n. But when you break up the integrals like this, especially when you're separated by just 1, it makes everything really easy to resolve. Also, just notice everything inside, we've got no x, we're just integrating all constants, so in every case, the constant is just going to come out front of the integral. And so what I want to do is we can actually, let's just focus on, I'm going to exclude the first and last one. So excluding this one, let's just look from here to here. For all these integrals, we have integer bounds upper and lower. And so instead, we already used n. So if I write this as like, say, k to k plus 1 of some constant value, and we integrate this, we just get, it's the same thing as integrating 1 from k to k plus 1. And what's going to happen is basically the whole integral is going to go away because when you evaluate this, you get k plus 1 minus k. This whole thing is just 1, and so we just get back the constant. And so for all these middle integrals here, all the way to this point, we're just bringing back the constant, and we don't have to worry about the integral. So before I try to put this all together, let's actually just calculate this one, because we can just calculate these because, again, it's just constant. So let's write this as, I don't know if I want to do this, but I just factored a minus out and write it as minus n plus 1. You integrate it, you get x evaluated from minus 2024 pi to minus n. Plugging in here, we have this minus n plus 1 in front. Then in for x, we have a minus in both these. Let me factor the minus out and write this as a plus. Then we're going to have here n minus 2024 pi. So let me just capture this as the first term in our whole big sum here. And then let me capture these middle terms. So it's going to be like minus n plus 1. Maybe let me kind of write it like this so we can kind of keep track. Then the next one is going to be minus n plus 2. Eventually, like you're going to have a 0 in the middle, and then at some point you're going to get to like n minus 2 plus this last one here, which is n minus 1, and then we just need to deal with this last integral here. So for this, when we integrate this, we're just going to have n out front as a constant. Integrate it, we get nx evaluated from n to 2024 pi. Doing this, we just have n times 2024 pi minus n. So we'll just take this, I'm going to add this to the sum here at the end, and let's see if we can put this together and finish it off. Okay, now here all that's left is I'm just trying to get some simplification, and everything in the middle we're going to get a lot of cancellation, like n minus 1 plus 1 minus n, that's just going to cancel and be a 0. N minus 2, 2 minus n, that's going to be a 0. And then that's going to go on and on, like you're going to have an n minus 3 and a 3 minus n, all the way, all it's going to cancel, everything's going to cancel, and the 0 is just going to be a 0. So all that's going to be left is this first term and last term and this minus n. And so in order to simplify further, one thing I can do is take a minus sign out of this. If I reverse the sign here, now this is n minus 2024 pi. So I can make this a minus right here. So then what's going to happen when I distribute this up is this is the same thing here as this right here. So if I distribute in the n plus 1, I'll have one term, n times n minus 2024 pi. Then distributing in the 1, we have a positive n minus 2024 pi. And then here we're going to have this minus n minus 2024 pi. And then on the end, we're going to have just this minus n. But now if you subtract this and this, you just get a 0. So we can cancel this off here, this off here. Rearranging this, we have n. I'll bring in this minus n minus 2024 pi, n minus n 0. And so for my final solution of this, we get minus 2024 pi. And so my real takeaway on this one is not so much this answer, but just notice this is exactly the same thing as our lower bound. In the other video, when we had something like minus n to n of the same thing, basically, well, in that case, when n was an integer, we found the solution of this was just minus n, the lower bound. And so all this is doing really is just saying it really doesn't matter if the bounds are integers or non-integers, you're still going to get the lower bound. And actually, it even worked in the video when n was going to infinity. Okay, I thought it was a pretty interesting case with the floor function. Just wanted to show the integer case and the non-integer case. Thanks everyone for watching today. Have a good day.